Hi, everyone. My name is Kunal Menda, and I'll be talking about the scalable identification of partially observed systems using certainty equivalent expectation maximization. We're interested in learning models of dynamical systems in order to enable autonomous agents to act intelligently. And so imagine we have this robot over here that is trying to decide between choosing this red or this green button. It would be useful if it could predict whether pressing this red button is going to take it to favorable or unfavorable states. Two real-world applications of such model predictive control are autonomous driving and, more recently, the COVID-19 pandemic. It would be great if we had a model that could tell us exactly how much we could reopen an economy while constraining the load on the healthcare system. So in learning a model of a dynamical system, imagine we're trying to learn the dynamics of this basketball over here. We would typically go out and collect a trajectory of how the states evolved over time. And what we would try to do is parameterize some model, f of theta, that predicted the next state given the current state. And then we would do maximum likelihood estimation. So we would try to find the choice of model parameters that maximize the likelihood of the trajectory that we saw. However, we're interested in systems that are partially observed. So imagine that this basketball was spinning, and so it has some angular velocity. A lot of us have probably seen a video of a basketball being thrown off a dam and know that if you introduce this angular velocity, it can dramatically affect the dynamics. And so in order to learn the dynamics in such a situation, we would need to reason about what the angular velocity was and would typically need to take the expectation and integrate out that quantity. And we would do this typically with expectation maximization, but this can be intractable in high dimensions. So we study a certainty equivalent approximation, where instead of trying to characterize the distribution over the trajectory of states that we didn't see, we simply look for the most likely explanation. So we find that this approach to EM scales very well, but can introduce a small degree of model bias, which we study in our experiments. And we study a system of coupled Lorenz attractors, so as a simulated experiment. And we also look at a real-world application to an aerobatic helicopter. So hidden states are a common challenge in learning dynamical systems. So again, looking at the COVID-19 pandemic, the hidden states over here are the true number of infections, the true number of recovered individuals, and perhaps an accurate estimate of the amount of social distancing. We would need these quantities in order to be able to learn accurate models. In aerodynamic systems, aircraft typically shed vortices into the fluid behind them, and those vortices can in turn affect the dynamics of the vehicle. Temperature is also a key variable that sometimes we may not have in our data sets. In financial time series, we might want to predict how the value of a company evolved over time, and we would ideally want to know its cash flows, the demand for its product, as well as its supply. But sometimes we may only have access to the market's perception of what the company's value is. So the problem statement here is that imagine we have some hidden state x of t that evolves over time. And what we have access to are observations y of t of that state, as well as the inputs that we drove the system with. So we want to perform system identification. So we want to learn a model, f of theta, which maps a state to the next state, as well as a model g of theta, which maps the state to the observation that we saw. So given a trajectory of observations y1 to t and inputs u1 to t, and a parameterized model, so f of theta maps the state and input to the next state, but corrupted by some process noise w, as well as an observation model, g of theta, which maps the state and input to the observation, but corrupted by observation noise, v of t. We want the maximum likelihood estimate of the model parameters. So we want to choose the model parameters that maximize the likelihood of the observations we saw. However, we would need to reason about what those hidden states were. So typically, we would try to integrate out of the joint probability distribution the trajectories over hidden states. The procedure for doing this is typically expectation maximization. So in the E step, we would hold the model parameters constant and then try to characterize the distribution over the trajectories of hidden states. And then using that distribution, we can compute the expectation for a new choice of parameters of the joint log probability of states and observations. We can then optimize this function to find a new choice of parameters in the M step. By iterating through these two steps, we will converge on a local optimum. However, for nonlinear dynamical systems, we cannot analytically compute this distribution over state trajectories. And so the typical approach to dealing with such a situation is to use something called particle EM. So over here, sequential Monte Carlo is used in order to approximately characterize the distribution over hidden states in the E step, and then in the M step, an update is made using that approximate distribution. However, this can be intractable on high-dimensional problems. A lot of work has gone into scaling this sort of an approach to a specific set of systems. But on a general problem, you can require a large number of particles in order to characterize the distribution well. And it can also be unstable because we're doing a stochastic approximation to EM. And it can require a lot of time or effort to get this to reliably converge. So in this work, we study the certainty equivalent approximation. So essentially what we're saying is instead of using sequential Monte Carlo to compute this approximate posterior distribution over state trajectories, what if we just looked for 1-point estimate? So if we looked for the most likely explanation? Well, it turns out that we can use nonlinear least squares to find this most likely explanation. And nonlinear least squares introduces tractability. It can scale very well to even high-dimensional problems, but this sort of an approach will introduce some degree of model bias, which we will study in our experiments. So the first thing to do in this approach is to characterize a negative log likelihood objective. So this is a joint objective over the hidden state trajectory, as well as the model parameters. So the first component of this objective is the observation discrepancy. So if we were to choose some set of parameters and some trajectory of hidden states, how well do those hidden states predict the observations that we saw? We also add the dynamics discrepancy, which said that if you have two states, x of t and x of t plus 1, and some choice of model parameters, then how well does x of t predict x of t plus 1? So we can find both the set of hidden states as well as the model parameters using block coordinate-ascent on this objective. So in the E step, what we would do is hold the choice of parameters constant and try to find the hidden states that minimize the objective. However, since we're typically dealing with a non-convex problem, to get this algorithm to converge, we will need to add a proximal regularization term. And so this term basically just says that don't stray too far away from the previous guess. Then in the M step, we hold that state trajectory that we just found constant and optimize the parameters, again, with a proximal regularization term. And we iterate between this E step and M step until we converge to a global optimum. This summarizes the certainty equivalent EM algorithm. So in experimental validation, we explore by comparing our algorithm to particle EM, the bias variance trade-off of making the approximation that we did, as well as performance. And what we study is a Lorenz attractor system. So this is a highly nonlinear system that has chaotic dynamics. So first, let's look at our algorithm alone and see what happens as we vary the amount of process noise and the amount of observation noise from the true system that we generate trajectories from. And what we find is that our approach is able to reliably converge to the global optimum with some small degree of variance. However, as we crank up the process noise in the true system, we actually find that our approach leads to some degree of expected model bias. We also find that from a variety of initial conditions, we robustly converge to the global optimum in less than 5 epochs of training. When we compare this to particle EM, we find that particle EM actually initially diverges from the global optimal solutions, but over time will converge over the course of maybe 100 epochs to solutions of a similar quality to ours. In terms of per epoch runtime, we find that our algorithm is able to run 47 times faster. And this is because nonlinear least squares can be implemented much more efficiently sometimes than sequential Monte Carlo. Let's see if these results scale to higher dimensional problems. So over here, we couple 6 Lorenz attractors together to get a highly nonlinear but high dimensional system. We find as one would expect, that as we give our algorithm more data, we converge to better and better solutions. We also find that our approach can monotonically converge to local optima, whereas if we look at particle EM, it actually diverges to solutions that are worse than the initial conditions we provided it. In the next experiment, we apply our approach to a real-world problem. So over here, we look at an aerobatic helicopter. So this is a helicopter that has done a ton of backflips and other maneuvers in the sky. But while doing so, it imparts a significant amount of momentum into the fluid around it. And so we need to reason about what the state of the fluid is if we're going to accurately predict its dynamics. So what we explore is, can we learn a neural network state-space model of the system using our algorithm? So the baselines that we compare against are first standard machine learning approaches. So let's just pretend like this wasn't a partially observed problem and try to map the states that we do know to the next states. So this would be naive regression, where we try to make this mapping with a neural network. We could also use an LSTM that would take a time series of all previous observations to try to predict the next observation you see. We could also use an approach from standard control called subspace identification. And we also compare it to the state-of-the-art approach, which we call the H25 model. And here, essentially what we're doing is taking the 25 historical observations and trying to use those through a neural network to predict the next observation. We note that this approach is not a state-space model. So our approach tries to fit a neural network, a state-space model, to this sort of a system to reason about what those fluid states could have been and use this to make predictions. So what we find is that when we look at trajectories in our test set, the model that we learned actually has the lowest RMS error across the board. So what we find is that certainty equivalent EM allows the training of a nonlinear neural network model that achieves the best accuracy. The takeaway here is that learning nonlinear dynamical systems from partial observation requires some form of approximate expectation maximization, and that certainty equivalent EM is a tractable algorithm that tends to perform well. Some future application areas that we're looking into are predicting the pandemic. So over here, we're interested in learning epidemiological models from the incomplete data that results from limited testing. We're also looking into distributed versions of our algorithm that can scale to even higher dimensional problems. With that, we want to thank you for the attention that you've paid.